Good morning. We started with equilibrium and shear force bending moment diagrams. And as I said, this is something that we need throughout the semester. Next week, we'll talk about determinate, indeterminate structures. And you will see that's how we define determinate versus indeterminate structures, whether or not we can analyze them and tackle them by just using the equations of equilibrium. But regardless, one of the main aims that we have is to find out about internal actions of a structure, namely axial forces, shear forces, torques, and bending moments. We will learn a few different methods, quite sophisticated methods, to tackle complex structures. But that's only to find the unknown reactions. Ultimately, even if we use those complex methods to start the analysis, eventually we need to draw shear force bending moment diagrams, because that's eventually what we need to be able to design a structure, which is the ultimate goal. We want to design a building, we want to design a bridge, a dam, a pipe support, a nuclear reaction building, a ship, an aircraft. We eventually need to know the internal actions. Shear force bending moments are the most important ones. Well, all the other ones, depending on what the structure is exposed to. So therefore, knowing how to draw shear force bending moment diagrams is essential. And that's why, as you could see, I've changed the order of lectures a little bit. So we make a quick start on shear force bending moments, and I gave you a self-assessment, and we started with shear force bending moment diagrams. And hopefully today we'll have time to work on shear force bending moments and equilibrium and free body diagram and the relationships between external loads, shear forces, and bending moments. Because as we touched on last week, there's a mathematical solid relationship between what we apply onto a structure and how the shear force and bending moment diagrams will look like. We integrate, we differentiate, and this is how all three of them relate. So ultimately, what we want to be able to do is to use those relationships to a lot quicker draw those diagrams. But this is the lecture that I used to start the unit with, because this unit is a structural analysis. So it's nice to know what a structure is. What do we refer to as a structure? And what are these external loads that we keep talking about, that when a structure is exposed to, causes those shear forces and bending moments and axial forces to develop inside these structures. Now, there's a few topics that I'll touch on today. Even though it's only one lecture, it's probably one of the most important lectures. And it's so fundamental because, as I said, we'll define what a structure is. Before you analyze a structure, there needs to be a structure. And as a structural engineer, you actually decide what type of a structure you're going to have. That's the first decision that you make. What material you're going to use and what form of a structure you're going to use. In terms of construction material, traditionally we had stones, rocks, and then later on masonry in terms of bricks. And we had timber, wood. But then gradually we added iron to the list. But soon we realized iron was not really perfect. It's a pretty strong material when you compare it with bricks, for example, in terms of compressive strength. But as you know from materials and manufacturing, I'm not sure whether Majid teaches these units or Lai Chang or a combination of the two, but they've talked to you about the structure of solid materials at a molecule level. And one of the things that they have probably talked to you about is that some of the materials are ductile, some of them are brittle. And iron is a good example of a brittle material. And brittle means that it can resist loads up to a point, and without any warning, it will suddenly collapse and fail. And as a structural engineer, we have a little bit of an issue with using brittle materials because we want to get some warning. It's like a doctor that looks for symptoms. When you refer to a GP, they ask you questions. They try to figure out what's going on, what is causing the problem, in this context, the failure. And they look for symptoms. And as a structural engineers, we also look for symptoms. And brittle materials don't give us that. They resist, and they suddenly collapse. So iron was found out to be brittle. Then engineers worked on it, and material engineers and structural engineers, and then added some other elements to it. A tiny bit of element can change the property of iron quite drastically. So we add carbon and other aluminium, and a long list of elements that we add to iron to manipulate its properties, and we make it a ductile material. So we need to make a decision what construction material we want to use. That's one of the first decisions that you need to make. Another decision that you need to make is what type of loads is the structure going to be exposed to. Like in Perth, earthquake is not really a dominant load on structures. Wind, on the other hand, is one. In some parts of the world, it's the other way around. Earthquakes are so strong, ground motions are so severe if they happen, that wind is almost nothing compared to them. We talked about dead load, the gravity, live load, and that sort of thing. So we need to make a decision. Sometimes it's hydrostatic loads, earth pressure. If you're digging out the dirt and you've got basements and things like that, then there's pressure coming from the soil surrounding the building. Where do they come from? How do we determine them? These are basic questions that you need to contemplate before you have a structure to analyze. The other important one is the form of the structure, and we will talk about it. But you may need some time to really read these notes again and again, look at other sources to find out more about the structural forms. But these are the basic decisions that you need to make, and only then it comes to structural analysis, and then it's design. So we analyze to find out what's going on inside different elements of a structure. Once we find the magnitude of shear forces, bending moments, axial forces, so on and so forth, then we design the structure for whatever material that we have decided. And that's when you come up with the size of the structural elements, the size of a wall, how thick the wall needs to be, how big of a column you need at this corner or in the middle or at that corner, how big of a beam or how deep of a beam you need, how wide it needs to be, how much rebars and steel you need inside a concrete structure, for example. I've put together a few definitions for structural engineering from different references. So let's quickly read them. A structure refers to a system of connected parts used to support or resist a load. And within that statement, you see a few technical terms. A system, what type of system are we talking? It continues to explain it a little bit. Connected parts. So its logo is not the best term, but it's something that we put together. It's not just one solid element. To support or resist loads. It's funny because loads do not really exist. It's a definition that goes hand in hand with the structure. So when we talk about, for example, dead load, the weight, the dead load mainly refers to the weight of the structure. So you can realize that without having a structure that doesn't exist, dead load. Or live load is these people, is us walking into a building. So before we have a structure, there is no live load. It comes to existence as soon as we have a structure. So it's a concept, or wind load. If you do not stand in the way of the wind, there is no wind load. There is wind load. It becomes load only because something is sitting or standing in the way. Earthquake, exactly the same. It's a natural phenomenon. It's just the ground motion. It translates to load only because we build the structures. An engineering structure roughly means something constructed or built. So it sort of says there is human factor in there. So we construct something and then we call it a structure. Structural engineering is a science and art. There is artistic element in it as well. If you ask me to design a structure and you ask another structural engineer to design a structure, in many ways there will be similarities, but it's very likely that they won't be identical. So there is that sense of artistic element based on scientific reasons in that process of designing and making. So that part is important. Somebody designs a structure, somebody makes a structure. So we design a structure, the structure doesn't exist. It's something that somebody starts that designing process. This building doesn't even exist when you start that drawing process on a piece of paper, and then somebody makes it. With economy and elegance, obviously we look at the how pretty the building is going to be. That's probably not the structural engineer, it's more the architect that looks after that part. And there are always fights between the structural engineers and architects until they compromise enough to be able to build a structure. Economy is another one. You may design a building in one city, and because of the access that you have to relevant industry and materials, you may design it in concrete, and the same building you're asked to make it in another region, and you will make it out of steel because of the labor available to you, the other parties that you need to make a building. So eventually you make buildings, you make bridges, frameworks, other structures so that they can safely resist the forces to which they may be subjected to. That's another thing that is part of the design, what type of loads the structure is going, and that's another reason that you may move from one material to another, because in one region the loading is going to be different from another region. Structural engineering is the art of modeling materials. So this is what we do. We model materials. Again, you're sort of familiar with that part. We draw stress-strain curves. We consider materials behaving elastically or plastically. Some of you have been pretty active in talking since I started. So please stop talking. We do not wholly understand. That's a fact. Concrete that we use is steel, timber, masonry. We do not know how exactly they behave. Even to date, we do not know how exactly they behave. There's a certain level of ignorance that we have. We literally do not know how exactly they behave. We have a good level of understanding, but it's not perfect. The way we understand masonry today is very, very different from the way we understood masonry 50 years ago, 70 years ago. So we do not know how exactly it behaves, especially when we come up with composite materials like reinforced concrete, pre-stressed concrete, timber concrete composites. So we design these buildings out of these materials, and we do not really know how the material is going to behave to start with. Into shapes we cannot precisely analyze. That's another approximation that we have. I will shortly talk about frames and trusses and things like arches. There's a certain level of approximation. When we draw a structure on a piece of paper, it's going to be very different from what is going to be built. So again, there is a level of ignorance there. Not ignorance as such, but lack of understanding, let's say. To withstand forces we cannot properly assess. That's another major part. The loads that we keep talking about, dead load, live load, wind load, hydrostatic loads. Earthquake is a major one. Blast, impact. It's really, really difficult to quantify these forces and loads that we use in our analysis. So we do not understand the material. We cannot really model the structure. We do not know how much load is going to be applied onto these structures. Yet we design them in such a way that the public at large has no reason to suspect the extent of our ignorance. So make sure out of this class you do not talk to anyone about how much we're ignoring when we are designing these buildings that we are using on a daily basis. But we've got mechanisms to eliminate a lot of the risks related to the structures if they were going to fail. So there are mechanisms that we apply and implement to make sure that they are safely designed eventually, despite this lack of knowledge. It's related to all sorts of engineering branches. And if we do not do our job properly, there will be consequences. It is not necessarily that if we do not do our jobs properly, it is the fact that the load that you estimate, the wind load or the load coming from tornadoes, cyclones, and things like that, we calculate those magnitudes based on the historic information that we have. And that historic information keeps changing. So inevitably, there will be some failures. So I've got some notes that I'll probably just leave it to you to have a read. For example, here I've listed pretty much the standard steps that we take to analyze and design a structure. One major part of it is to determine, as I said, the types and magnitude of loads. So there are some questions, fundamental questions there. And the way we have gone about it is that in any country, we've developed standards that we use to calculate, well, first of all, to determine what type of load we're exposed to. This is really important. So we use these standards, just listen up please, to determine what types of loads we need to consider in our analysis, how to combine them, and what the magnitudes are that we need to use. Because there's another fundamental question there. We know that there is dead load. Dead load is the weight of the structure, and anything that is not moving, we categorize that as dead load, like the chairs that we have installed here, the carpet, everything that you see, all the architectural decorating elements that you see, plus the weight of the structure. So that's a dead load. As I said, we call it dead because it doesn't move. Then we have live load. In fact, if you were doing engineering probably 70, 80 years ago, even more recent, 50 years ago probably, definitely before I did engineering, but I don't know when exactly, everything else was categorized as live load. So we had only two main categories, dead load and live load. And everything else would be a subcategory to live load. So wind, earthquake, hydrostatic, everything else would be part of the live. Snow, ice. Now, these may sound a little bit strange in Perth, but if you were doing engineering in Canada, for example, ice would be one of, and you were designing, in fact, I remember when I was a student, I emailed a professor in University of Alberta, I think it was in Canada, and a PhD topic that he proposed to me had got something to do with the ice on cables, how to go about it. So ice, snow, these are also different types of loads that we may not consider in Perth. So we use the standards to determine what types of loads, and also the magnitude. Because for an individual engineer, it's really difficult to calculate how much live load are we going to consider here. So these all come from relevant standards. So we refer to a standard, and we'll see some examples. There's a table. It tells you if you are designing a classroom, this is the live load that you need to consider. What are the KPA? You consider kilopascal KPA as live load. And you pick that magnitude and you put it in your analysis. And then you're safe. You can defend yourself. If something goes wrong and they take you to the court and they look at your report and they see that you've used the right value, you did the right analysis, then you're safe. One thing that you need to be quite vigilant about is that these standards get revised every few years. And you need to make sure that this morning, if you're calculating the live load today, this morning, you're using the most recent version of that standard. If you do not check it quite regularly, there's a chance that you may be using the older version. You might have used an older version last year. Within that time frame, the standard may get revised, and then this year you must use the new version with some of the values might have changed. So it's your responsibility to make sure that you are using the most recent standard available to you at the time of your design. That's another important point. And there's another question that you need to answer, and that is, how are you going to combine these effects? We know that there is dead load, there is live load, there is earthquake, there is wind, there is whatever else. The fundamental question is, are they all going to be applied at the very same time with the full capacity? Meaning, everybody is sitting here when the most strongest possible wind starts to blow. And at the same time, we have the rarest ground motion happening at that very same time. Is that possible? If it's not possible, then the question is, how are we going to combine these? Not only that, there are design philosophies that I will quickly talk about towards the end of the lecture. Okay. So live load is one type of load that we need to look at. In fact, in a few weeks' time, we will look at another topic. If you look at your schedule, it is called influence line. Because when it comes to live load, the funny thing is, yes, we determine, okay, how much the live load is. But another fundamental question is where the live load is going to be, because it's live. When you're designing a bridge and you expect that train to pass over that bridge, is it the whole bridge that is on is it the whole train that is on the bridge? What if it's in the middle of that, what if it's in the middle of the bridge? Basically, only half the bridge has got the train on it and the other half doesn't have the train on it. Which one is going to give me the most severe case for my analysis? And we will talk about it. Sometimes it's not when the bridge is covering the whole bridge, the train is covering the whole bridge. Sometimes it's even worse when the train is only on the first half of the bridge for some of the actions. So you see, it becomes a complicated process to analyze this structure. Wind is another one in terms of the types of loads that we have, and you hear it on a yearly basis. In some part of the world, wind has got so much damage to the society. This is an interesting YouTube clip. You can find it online. It shows a beautiful bridge was built, very briefly, a few decades ago. And on the day of commissioning the bridge, there was wind. And it collapsed. And you can see it's moving like you cannot even imagine. And that was the start of the next era of looking at dynamic loads and how we design and how we treat dynamic loads. And dynamic, I mean, mainly wind and earthquake. But these days we look at blast and impact and all of that. So you can watch them and see what's going on. Earthquake is another one. It depends on the region where you're designing the building. In some parts, earthquake, as I said, is quite severe. In other parts, it's not as severe. When the earthquake happens, it's basically the ground motion. There are waves in the ground, and the ground is moving. But the ground can move in any direction. That's one of the characteristics that makes it quite complex. So you do not know if the earthquake is shaking the building in this direction or that direction or that direction, and it'd be a combination. Not only that, but it's got vertical direction as well. There've been earthquakes in the past where the vertical component was actually even more severe than the horizontal motion. And the scary part with the vertical motion is that when it's pushing the building up, let's say the maximum acceleration is equal to g, gravity. It's not always that strong, but sometimes it is. But as an example, just assume it's g. So when it's pushing the building up, basically everything is twice as heavy, because there is g already acting on the building. Now there's another g pushing the building up. Everything is resisting, yes, inertia forces. So if you are 50 kilos, at that very moment you become 100 kilos. So the weight of the structure basically becomes double. When it goes the other way, there's no weight. And just imagine in your head, because we're all familiar with gravity, how disturbing that concept is when you are designing a structure. So that's something to consider. And lateral or horizontal motion is another. It translates to like pushing the building in one direction in a fraction of a second, and then pushing the building in the opposite direction, and then push it in the perpendicular direction, and then pushing it in the other direction. So it's really complex in terms of loading, how the load itself behaves. And just to add to that complexity, you cannot find any two earthquakes that are identical. So you're dealing with something which is completely unknown. Now, based on historical records, we can come up with some ideas of how it's going to behave. But the fact of the matter is that we do not know how it's going to behave. What was the question?
Are all live loads part of external loads? So looking at structure, internal and external loads. Live loads part of the external load.
Mm-hmm. What do you categorize as internal?
The internal stresses of a particular, say, beam.
Okay.
External stresses.
Something that I normally do in my classes is to correct you how you formulate your question. And the reason is, especially with the technology today, you're in the office, your phone rings, and then you pick up the phone, and another engineer starts talking about very specific. They are erecting a steel structure, and the guy wants to know about whatever, about beam 3 on axis A2, level 5. And we're talking about a structure with hundreds of members. So there's a problem with the installation. The beam is in the air. The expensive cranes are holding it up. The crew is there. He's on the ground. He's got a question. He's calling you. And within less than a minute, he needs some answers from you. And he's speaking engineering language. It's not necessarily the everyday English language or whatever other language that you may be talking. It's an engineering version of it. Stress, internal, external, force, load, these are all specific terms, and each one refers to something else. Stress and strain, a good example. You know what the stress is, what the strain is. One has got a unit of MPa, stress, force divided by area. Strain is length divided by length, no units. If you talk to a psychologist or just someone off the street, strain and stress in some contexts may sound something very, very similar. Not exactly the same, but if you confuse the two terms, they still understand what you say. In engineering world, if you use the stress instead of strain, it's a completely opposite meanings. So sometimes, and you are still doing your engineering degree, so I don't expect you to pick those words ideally, but let's have a conversation about that. So let's start again, and I'll try to make sense, and everybody else as well. So that seems like a good question. Let's start again. Is a live load
all live loads part of the external
loads?
Loads.
You see, you just interchangeably use stress and loads, and we cannot do that. Stress is something that happens, let's discuss it, based on what we know already, but let's use them correctly. Stress is something that happens inside a structural element. You've got a beam, you push it down, it flexes, and then not any stress, but flexural or bending stresses start to develop. That's a stress. Stress is always inside the material. And that's why I refer to axial force, shear force, bending moment, these as internal actions. They do not exist. You do not see them. They are how a structural element responds to an external load. So load is something that is imposed on a structure, is applied onto a structure. Yes? Loads can be in the form of point loads or forces, distributed loads, a torque, which is a twisting moment. It's not internal. Something is causing that twisting. It's a moment, we call it torque. We are a little bit more specific when it's causing torsion. This can be external. This can be an external load. Dead load, I think I know what you mean, so I try to explain a little bit, and then you tell me if I'm answering the question. The only load that we can probably refer to as, it's not the only, internal, I would say, is the gravity. Because when you make a structural element, the weight comes with it, and that's also a load that we need to design it for. It becomes part of the loads on the structure. So in that context, you can refer to it as internal. We don't really categorize them in that sense. We categorize them in more on the basis of how they behave. So I want to change your perspective a little bit, so you look at it from another perspective, which is more standard when you design a structure. But as I was trying to guess what your question is, I remembered another type of load, which is quite important for larger structures like dams, bridges. Can somebody guess what I'm referring to? Because I said larger structures. For example, when there is winter and there is summer, there's some change. There's something that is changing. Expansion is not a load. If you want to refer to it as load, we refer to it as thermal effect or thermal load. That can be internal in the way you are formulating the question, I think. And I think it's probably only that. In the context of load, because there is other damages that can start from within the structure, but it's not really a load. That's degradation of the structure. But thermal. So we don't really categorize it that way. My answer may not be comprehensive, Liz, but I can only think of gravity and thermal that start from within, if you like. But it's mainly dead versus live, because dead we know, because we can sort of deterministically say this is where the dead load is, whereas live load we never know. If I threw a party here and I had a big table of food here, nobody would go to the last row of the seats. Everybody would be, it's the same number of students, but everybody will be here. That's the problem with live load. You don't know where exactly it is. And that's an important aspect of it. So try to look at it from that perspective. Good question. You see, whatever question that you ask, it triggers a few things that we can discuss. Terminology, and other things that we just, so thanks for that. I would give you 2 extra marks in the final exam, only if I remembered that you asked this question.
1-0.
I would, I would remember, but yes.
What's the relationship between live load, dead load, and then static loads?
Live load, dead load, and static loads. Yeah, that's another very good question. Remember, now I'm taking my time just discussing the structural analysis and structural engineering, so I'm not going slide by slide. And that takes me to another comment that I made last week, that you need to look at your lecture notes. You need to read. I'm only 15-20% of the job. The rest is with you. So you need to do your homework. You need to do the tutorial questions, examples. You need to study and come to this class with questions. That's the best way to make use of this class. There's another way of categorizing loads. We have another two categories, static loads versus dynamic loads. For everyday structural engineering, the majority of cases, we only deal with the static loads. Even when we design for earthquake and wind, which are in nature dynamic, they are moving, yes, there is inertia involved. We use approximate methods to estimate them, and we use equivalent static loads. But if you are dealing with a complex structure, like the one that I just mentioned, a reactor, a nuclear reactor building, or a high-rise building, that approximation becomes too rough for that type of structure. Then you must do dynamic analysis. If you look at earthquake standard in Australia, 1170.4, it gives you different avenues, different methods to estimate and apply earthquake loading on a structure to design. One is called equivalent static loading, which is a pretty, compared to the others, easy way of approximating earthquake loading. So in that way, earthquake becomes static, but it's not, it's dynamic. But we have developed trustworthy equivalent static loads to estimate actual dynamic earthquake loads to be able to design the building for ordinary buildings. Each and every standard that you pick up to use, one of the first pages is called scope. That's another important, it's normally one page. It tells you when and where you can and you cannot use that particular standard. For example, wind load, 1170.2, I think there's a limit of 200 meters, I might be wrong, but it's got a limit on the height of the building. If the building is higher than that, you can't really use that as standard. You have to use another way of estimating the load. This particular building, there was another story there. We refer to it as soft story, because in that building there's a combination of masonry walls and reinforced concrete frames, and during the earthquake, that column, probably 3 meters long, is completely gone. So you can see 2 floors now, well, 1 floor completely gone. Liquefaction is another one that may happen if when you construct a building on a sandy soil, that liquefaction can happen. Liquefaction is when, because there is always water table and there is water inside the ground, yes? So when the earthquake happens and it's moving the sand and the ground, at some point the sand may behave like just water. So all because it's a porous material, yes? So if all these little voids are connected inside the sand, then it becomes basically water. And sometimes you see buildings similar to that. It seems like an intact building, just too tired to stand and lying down. That's because it's sitting on sandy soil, and that liquefaction has happened. Over a few seconds it may just happen. And then it's like you've got a building in a pool. So it just becomes like that. And you can see a few of them have had the same experience. The same thing has happened here. Wave, if you are designing an offshore building, then waves, that's one of the loads that you need to estimate and calculate and then design the structure for. Impact, blast, you don't design a residential house for impact coming from an airplane. But again, if you're designing a sensitive structure, like as I said, a nuclear reactor, then you do actually design them for an impact coming from a jet just flying into the dome, because you don't want to have failure even in those extreme cases. This is this is a very rare example of impact if you fall asleep or you do not drive carefully. I'll leave it to you to have a read about Australian standards and what they are and how they are developed and how they are revised. These are some of the important ones. I do urge you to, for now as a student, you have free access to all Australian standards through library, because these are pretty expensive documents. And I urge you to download AS 1170 series. So we have 1170.0, 0.1, 0.2, 0.3, 0.4, 5 standards. Do download them. As you can see, each one of them talks about a different type of load. So 0.1 is dead and live loads. We will have a look. 0.2 is wind loads. I will talk to you about it in steel design if you're a civil engineering student, or if you're mechanical, you want to do steel design as an elective. I've had mechanical students in my classes in the past. Snow loads are not really relevant to most of Australia, and earthquake is 0.4, which I'll talk about in another unit, civil engineering design, which comes after steel and concrete design. The fact that I'm just skipping these slides, it doesn't mean that these are not important, but these are the type of slides that you can read on your own. So in 1170.1, it's one of the tables that you see, just to have a taste of what you see in that standard. This one talks about the, not density, but weight per cubic meter of different materials that you can use in your design. So if you've got aluminium, you use this particular number given in the standard, not any other number that you may Google, because you want to make your design based on Australian standards, if for nothing else, to protect yourself if something goes wrong. You can demonstrate that you've complied with NCC, National Construction Code, and you've used the appropriate standard to estimate the loads. This is another table. It's slightly different. The numbers that are given here are kilonewton per square meter. The previous one was per unit volume. This is per square meter. And that's why you see a mention of thickness. For example, gypsum plaster, every 13 millimeter of it is 0.13 kilonewton per square meter. So, yeah, so the table is slightly different from the previous one. I've got another example for live loads. Huh?
Those forces like the ceiling and all that, would that include a wind safety factor, or is that just there?
No, there's no safety factor there, no. Again, safety factor, it's a beautiful concept to talk about. Let me see how I go with the rest of the lecture. I may talk about it briefly. So, as you can see, this is talking about imposed is another term interchangeably used for live load. So, speaking of that phone call with another engineer at site, if you say imposed load and he says or she says live load, that's okay. They mean the same thing. But if you mix up stress with the strain, or stress with the load, or force with whatever else, they are not interchangeable. So as you can see, there is a category there, domestic and residential activities, areas where people may congregate. So then there are subcategories, and they talk about, for example, classrooms, very relevant to what we are doing here, classrooms. For classrooms, uniformly distributed actions, KPA is 3. 3 KPA. What does it mean? 3 kilonewton per square meter. So per square meter, a meter, so that sort of area, just to make sense how big of a load it is. And it says 3 KPA, 3 kilonewton. 3,000 newtons. That translates to approximately 300 kilos. An average person about 70 kilos, let's say 75. That becomes how many people? 75 times 2, 150, times another 2, 300, yes? So in 1 square meter, the live load that is recommending to use is approximately 4 people in each square meter. So it's pretty dense. 4 people standing next to one another. Yes?
Is that including the weight of like flooring and
No. That is live load. Just a live load. Nothing else. Nothing else. Very good question. It does include your clothing, but nothing else. So again, that's something that you need to exercise. Whenever you see a number, try to make sense of it. So classroom, 3 KPA. But you see, you've got 2, you've got 2.5, you've got 4. It also recommends a concentrated action, which is a point load. Again, for classrooms, it goes up to 2.7. So again, you have to design it for a point load of 270 kilos, but not distributed. There's one example here. I'll skip it for now. Actually, do you want to do it now? Do you need a break? Oh, that's good. Nobody needs a break. Do you need a break? Just 2-3 students, so we don't need a break. Do we need a break? So how many times does it take me, just so I know for next time? 3? Okay. 3. Let's have a 7-6 minutes break. So within 10 minutes I can start.